We good? Okay. Can everyone hear me okay? Yeah, let me know if, okay. All right, so I'm going to violate long-standing tradition that every good number theory talk should start with an elliptic curve over Q, which might seem strange given that the Sato-Tate conjecture is all about elliptic curves over Q. But I think it's actually very instructive to go through an even simpler example, one that is so familiar to many of us that it almost seems trivial, but if you dig into the details, it's surprising how much of the structure of the more general problem you can see even in the case of a variety of dimension 0. So let's get started. Okay, so Sato-Tate in dimension 0. So we're going to start with a square-free polynomial with integer coefficients. Call it f. For each prime p, we can reduce the coefficients of f mod p. We'll get a polynomial over the ring z mod pz, which we'll identify with the finite field with p elements. And we're going to be interested in the quantity nf of p, which we'll define as the number of roots that our reduced polynomial has modulo p. Or you could think of this as a variety of dimension 0, and we're just counting the p points on the local fiber. Okay, so as an example, let's take a particular polynomial, say this cubic. And so we could, for various primes p, we could go and compute nf of p. So let's do that for a few primes. So if you quickly count roots here, mod p, if you're very fast, you can do this as fast as I'm writing them. Okay. All right. So everyone see the pattern? No, it's kind of hard to see the pattern for two reasons. One is I haven't given you very much data, but even if I gave you a whole lot more data, there's actually not any pattern. We know the splitting field of this polynomial is an S3 extension of Q, and so we shouldn't expect any obvious pattern. But nevertheless, we could still look for sort of a big picture pattern. So let's define a quantity Cp of b. So b here is some bound, a real number or an integer, whatever you like. And we'll define this as the ratio where we're going to count over primes up to b, our bound, and we're going to look at the quantity, how often the quantity, oops, I've mislabeled, this should be an n. Okay, how often we see exactly n roots of our polynomial mod p. And whenever I write p less than or equal to b, I always mean that p is a prime. And so now we could, for increasing values of b, we could compute these quantities, these CNs. So let's do that. And of course, this number nf of p, this is some integer between 0 and whatever the degree of f is. So if we went up to 1,000, say, and I'll let you do this in your heads real quickly, we get this. That's a 2. Okay. Well, again, looking at one value of b doesn't tell us much. We're interested in what happens asymptotically as we let b head towards infinity. So let's do that. And we could even go up to 10 to the 9th. One of the great things about these varieties of dimension 0 is it's easy to count points on them. So we can work with quite large values of b. Okay, so now at this point, I think it's reasonable to say that we do see a pattern. And we might conjecture that as b tends to infinity in the limit, we're going to see these rational numbers. Now, of course, as number theorists, we know not to be surprised by this. So if we consider the set of q bar points on our zero-dimensional variety, Well, we know that this comes equipped with an action of the absolute Galois group. And there's an associated Artin representation that we're interested in. Okay, so this is going to be a representation I'll denote rho sub f. It takes an element of the absolute Galois group. And it's, oh, sorry, thank you. Okay, I'm almost done with this page. And it spits out a matrix, an invertible matrix, d by d, where d is the degree of our polynomial f. And for this particular Artin representation associated here, that d by d matrix is actually going to be a permutation matrix. Now, of course, I've written this as a representation of the absolute Galois group. But we know that it factors through a finite quotient, namely the Galois group of the splitting field of our polynomial. And you could take that as a definition of an Artin representation. It's exactly the representations that have this property. Okay, so d is the degree of f. Okay. All right. Okay, but it's going to be convenient to work with these absolute Galois representations because for us it's easy looking at f to know what this field L should be. But in general, when the situation is more complicated, we may know that it factors through some finite quotient, but we may not know what that quotient is. We may not know what the field L is. So it's convenient to work more generally with representation of the absolute Galois group. And when we're doing that, we're going to often want to be able to work with what's known as an absolute Frobenius element. A notion I'm sure is familiar to many of you, but for the sake of concreteness, let's go ahead and give a definition, because it's very important that we know exactly what we're talking about here. So we're going to take a prime P. We're going to pick a prime, call it frac P, lying above P. It's a prime of Q bar. What do I mean by that? I mean an absolute, a maximal ideal in the ring of integers of Q bar. Now, of course, there are infinitely many choices we might make, but pick one of them. And we have a reduction map from the ring of integers of Q bar down to the algebraic closure of Fp. Call this reduction modulo our chosen maximal ideal frac P. So we could take this frac P as precisely the kernel of this reduction map. And we have a decomposition group, which I'll just recall. These are the elements of, the absolute Galois group that fix our ideal frac P. And we know that we have a surjective homomorphism from the decomposition group onto the Galois group of Fp bar over Fp. And of course here by Fp bar I mean precisely the Fp bar that we chose here when we fixed our frac P. And we're going to take our absolute Frobenius element. We're just going to pick some element of this decomposition group, doesn't matter which one. The only thing I'm going to insist is that it gets mapped under this homomorphism to the Frobenius automorphism, which we know is a canonical generator for this Galois group. Okay? So this is certainly in no way canonical, this absolute Frobenius element, but it has the following wonderful property that for any, say, finite Galois extension, if it's unramified at P, well then we have a unique conjugacy class, which I'm going to denote conj sub L, associated to our absolute Frobenius. Actually, that's not a frac, that's just a regular P. So this is some conjugacy class in the Galois group of L over Q. And it contains, so we're in the unramified situation, so we have an isomorphism here. where now Q is my prime. I'll take the intersection of my frac P with the ring of integers of my Galois extension L. And we know that if I take my absolute Frobenius element and restrict it, so it's a Galois automorphism on Q bar, so it's an automorphism of Q bar, but I could restrict its action to L. That's going to give me an element of the Galois group of L over Q. And I'll denote that element, say, call it sigma sub Q. And it's going to get mapped to the Frobenius automorphism. Okay, so we could think of this absolute Frobenius element as determining an infinite tree of Frobenius conjugacy classes in each finite extension of Q, Galois extension of Q, and the key point is that they're all compatible. Okay, but for us, the absolute Frobenius is an element of the absolute Galois group. And so it makes sense for us to talk about plugging it into a representation of the absolute Galois group, regardless of whether we're talking about a ramified prime or not. We can't say anything about what happens at the ramified primes, but we don't care because there are only going to be finitely many of them for any particular finite extension. Okay, and then the key property that we're interested in now is that if I want to compute this quantity, the number of roots my polynomial f has mod p, well, how would we do that? Well, we would use our Artin representation, Galois representation given by the action of the absolute Galois group on the Q bar points of our variety. So I'm going to plug it into the representation. That's going to spit back a matrix, and it's a permutation matrix. Now, the number of FP rational points are, by definition, the number of points that are fixed by the Frobenius automorphism. In other words, they're going to be the number of points that are fixed by this matrix, this permutation matrix. And if we want to count the number of points fixed by a permutation matrix, we just take the trace. All right. Now we're going to recall Chebytarov density theorem, which tells us that whenever we have, I'll do this for an arbitrary base field K, at the moment K is Q. So we have a finite Galois extension, let's say with Galois group G. And we know that for every conjugacy class, say C in our Galois group, if we compute the limiting ratio, say as B goes to infinity, where in the numerator we're going to count the number of primes, and I'm going to, since we're now working over, our base field is now a number field, I want to count the number of primes with norm at most B, and I want to count only those primes with the property that when I look at the corresponding conjugacy class determined by the absolute Frobenius, so this means I look at, as we noted up here, I look at the conjugacy class in the Galois group of L over Q that I get by restricting the action of Frobenius to L. Okay. And then in the denominator, I'm going to have just the number of primes of bounded norm up to B. And Chebyshev theorem says that this is equal to the cardinality of my conjugacy class over the cardinality of my Galois group. Okay. All right. And so with this in hand, we can completely answer our question. We can compute these, the distribution of NF of P for, say, for our specific example. So we had this cubic. And we know that its splitting field L is an S3 extension. Well, maybe we don't know that, but we compute it. And that turns out to be true. And from that, well, now we just need to ask about, so if we take the standard representation of S3 as 3 by 3 permutation matrices, all we got to do is figure out what the traces are. So we know that if we look at the conjugacy class in L determined by our absolute Frobenius element, well, there are three possibilities because there are three conjugacy classes in S3. One possibility is we could get a 3-cycle. So that matrix, and I check the trace and it's 0. And I say, how often does that happen? Well, there are 2 3 cycles in S3, so that tells me that C0 should be 2 over 6 or 1 over 3. Another possibility is I could get a 2 cycle. And then I compute the trace here, and I see that it's 1. And that tells me that C1, well, there are 3 2 cycles. 3 over 6 is a half. And then the last possibility is maybe I get the identity. And the identity has trace 3. And there's only one identity, so the ratio of the size of the conjugacy class over the size of the group is 1/6. And so this recovers exactly our conjectured limiting distributions. Okay? Great. So we're going to call this group, let's denote this, so for this particular F, the Galois group of its splitting field told us the distribution of NF of P, the asymptotic limiting distribution. So we'll think of this group as the Sato-Tate group associated to this zero-dimensional variety. So in our situation, it was, say, S3. And I'll note that since we're talking about Artin representations here, they're always factoring through a finite quotient. These are always going to be finite groups. So in particular, they're compact. And that means, like all compact groups, they have a Haar measure. And this is the unique translation invariant measure. So translation invariant just means that if I take any set S in the group and pre-multiply by some element or post-multiply, doesn't matter. Since we're in the compact situation, left translation invariance and right translation invariance are the same thing. And I'm always going to assume with our Haar measures that we are normalizing so that the whole group gets measure 1. Okay, and once I've made that choice, the Haar measure is uniquely determined. Okay? And now now that we have a probability measure, we can do things like compute expectations. So we could ask, for example, what's the expected value of the trace? On average, what is the average value of NF of P as P tends towards to infinity? Well, we can compute that by integrating against the Haar measure. So we're going to integrate over our group. The function we're integrating is the trace, integrating against the measure mu. Now, for finite groups rather, an integral is just a sum. So we're just summing over the elements in our group. What are the traces? Well, we want to think of this as a sum from n equals 0 to d, and we know the trace is going to be equal to the number of fixed points, n times the probability that we get that particular element. And this probability is 1. As you can, well, if you are used to thinking probabilistically, this fact is obvious to you. If you're a number theorist, you immediately want to start counting things and computing formulas and proving identities. And this might seem like a really cool fact that's not so obvious, but I'll leave it as an exercise to figure out that it is obvious. And this value is also equal to the limiting ratio we get if we were to compute this quantity. So we're going to sum over primes up to b, NF of p, over sum over primes up to b of 1. So this is also equal to 1. Okay? And we could more generally compute the expected value of other functions, like, say, powers of the trace. And we could even consider moments. So we could consider the sequence that we get by computing expected values of powers of the trace. So think of this as a sequence indexed by non-negative integers. And we could write down the moment sequence associated with this distribution. So for our S3 case, we take the moment sequence of the trace. We get, well, the 0th moment is 1, and then 1, I'll leave this as an exercise to figure it out. You all want me to write 42 here, but it's not 42. Okay. Now, it might seem like the utility of having moment sequences is that as long as your probability distribution satisfies certain standard properties, which all of ours will, the moment sequence uniquely determines the distribution and vice versa. Now, it might seem kind of silly here because we have a finite probability distribution that was determined by those 3 rational numbers. What do I need a moment sequence for? Well, I guess you don't, but when the probability distribution, when our G is now infinite, and our probability distribution might be a whole lot more complicated, The moments aren't any more complicated. They're still just a sequence of integers that uniquely determine the probability distribution. So working with moment sequences can simplify our lives a lot. Okay. All right. So I guess I want to cycle these through. Okay. So, yes, please. Excellent question. So the question was, what does the power of the trace count? Well, let's think about it. We could think of it as that's going to be the power sum of the eigenvalues, if you like. That would be one way to think of it. Another way to think of it, though, would be it's counting. I could think of it as taking. Well, I'm going to come back to that point because we're about to define a zeta function. So I don't want to get ahead of myself. But the answer, you ask a good question, the answer will become clear. Okay. So why might we be interested in powers of the trace, or not so different, traces of powers? So let's consider polynomials of slightly higher degree. We solved the cubic case. And I should mention, obviously we happen to pick an S3 cubic, but there are 3 other different types of cubics I could have written down, right? I could have written down a cubic that had whose splitting field was C3, or I could have written down a cubic that, say, split completely over Q, and so its splitting field was trivial, or I could have written one that split over a quadratic field. So there are actually 4 different subgroups of S3 that I could have gotten, and each would have given me a different distribution, different quantities for C0, C1, C2, and C3. And I could compute those in exactly the same way, just by writing down 3 by 3 matrices and computing traces. Okay? So we've now also completely solved the classification problem. What are the Sato-Tate groups that arise that are associated to cubic polynomials? And the answer is there's exactly 4 of them. And the 4 distributions we get can be computed explicitly by we're just looking at subgroups of S3. Notice that all 4 of those groups are subgroups of the generic case. If we wrote down a cubic polynomial at random, we would generically expect to see S3. All the smaller groups are special cases. And that phenomenon will carry over in general. Okay. But computing traces is not always enough. So in the cubic case, it completely just tells us everything we want to know. The probability distribution is determined by that. But let's look at a quartic case. So now for this particular quartic polynomial f, now our Sato-Tate group is going to look like C4. But for this other polynomial g, I'm going to get C2 cross C2. Okay? And if I compute the quantity C sub n, I find that C0 is 3/4, so 3 out of 4 times I get no roots at all when I reduce mod p. I never, except at ramified places, but we're going to ignore those. I never get 1, 2, or 3 roots, and 1 out of 4 times it will split completely into 4 roots. And so I get the same probability distribution associated to both of these polynomials, but their Sato-Tate groups are different. And I'd like to be able to detect that difference. Okay. So now we want to generalize our NF of P notation. We're now going to define NF of P to the R for any positive integer R. So we'll define this as the number of points we get when we now are going to look over Fp to the R. So we're going to take our polynomial, reduce it mod P, and then we're going to base change it to the degree R extension of Fp. Think that way if you like. And we want to know how many roots we get when we do that. And if we compute this for our 2 examples, well, NF of P squared is going to be, well, it's either 2 or 4. Okay, so it's going to be 2 when P is not a square mod 5. And it's going to be 4 when P is a square mod 5. Okay, and this corresponds to just which element of the Galois group we're going to hit, which Frobenius element we're going to hit. On the other hand, with our cyclic polynomial, with our C2 cross C2 polynomial, if we go to a degree 2 extension, it's always going to split completely. And so we're always going to see 4 roots. Okay. So we can distinguish these 2 cases by counting points over Fp squared. And in general, and now how would we compute that count in terms of our Artin representation? Well, remember our Artin representation is telling us the action of Frobenius. When we want to, and we're counting the number of fixed points over Fp. But if we wanted to count the number of fixed points over p squared, we really want to apply the p squared power of Frobenius, or another way of thinking it is we're going to take the square of our matrix, and in general, we could take the image of our absolute Frobenius element. If we take its rth power, that's just some other permutation matrix, and we compute its trace, that's going to tell us exactly the number of points that we get that are fixed when we go to Fp, the finite field Fp to the r. Okay, so this quantity here is going to be of interest. Okay. And of course, this is only for, I'm always going to be restricting to unramified primes. So this is for p not dividing the discriminant of f. And so this leads naturally to the definition of the zeta function. Because in general, depending on the degree of f, we might need to compute these nfp to the r's for larger and larger values of r. So let's compute all of them. So we're going to package these up into a single generating function called the local zeta function of f at p. Okay, so this is going to be defined to be x of, we want to take sum over r going from 1 to infinity. So we're going to compute nf of p to the r. Okay, so this is our exponential, our generating function. You could just think of this as a way of encoding this infinite sequence of nf of p to the r's. Now this, you might wonder, at first glance, this looks like a strange generating function. It's not an ordinary generating function. It's also not an exponential generating function, although it kind of looks like it, but I don't have an r factorial in there. But this definition is the right definition. It's sort of forced on us if we wanted to have some nice properties. I'll just note one of those properties now. We'll see the other one in a minute, which is that if f and g are polynomials with no common factor, well, then that means that their product is square-free. So this was a zeta function. As always, f is square-free. So the product is square-free, and that means it has a zeta function. And if you stare at this definition of the zeta function for a moment, you'll see that it's exactly the definition you want if you want this to be true. Okay. All right. Okay, so now we have this zeta function that we've written down. It's encoding these point counts over finite fields of increasing all the extensions of Fp. Now, a priori, this is just some exponential, this is some power series in T with integer coefficients, but I claim that it's actually a rational function. In fact, I claim more. So my claim is that this zeta function looks like 1 over a polynomial, which I'm going to denote LP of T, where this LP of T it's an integer polynomial. Its roots lie in the unit circle. And it satisfies a functional equation, or rather, it's a reciprocal polynomial in the sense that if I take the inverse of any root, it's also a root. Another way of saying that is it satisfies this functional equation. Okay? So I've made 3 claims here. I've claimed this zeta function is a rational function. I've claimed its roots lie in the unit circle. It's also known as the Riemann hypothesis. And I've claimed that it satisfies a certain functional equation. Okay, so those of you who are familiar with the Weil conjectures will be familiar with all 3 of these claims. So let's do as Deligne did and prove them, all 3 of them. Okay. All right. So maybe I better get a new page while we prove the Weil conjectures. Okay, so in dimension 0. Okay, well, so for any matrix, the remarkable thing about this proof is there's actually no number theory involved. Not only that, there's not even any linear algebra involved. So if I take any matrix, D by D matrix, invertible matrix with complex coefficients, I have the following identity. This is, I think, one of your exercises is to prove this. Now, at first glance, that might look like it requires some linear algebra, but these are just, you could think of these as an identity in the power series ring over symmetric functions, right? I could just identify my matrix by, just write down the eigenvalues. On one side, I have this, not quite its characteristic polynomial, but something that I can express in terms of the elementary symmetric functions of the eigenvalues. And on the other side, I have something whose coefficients are going to be expressed in terms of power sums of the eigenvalues. And we know from things like the Newton identities and lots of other combinatorics that there's a way to relate these things. And so if you expand these out in power series and compare coefficients, you'll find that this identity holds for any matrix. Okay. So now let's apply this to our particular case of interest, where we were working with a permutation matrix. So, well, we know that what it tells us in this scenario is that if we take our absolute Frobenius, plug it into our Artin representation, and we compute this determinant, okay, we're going to get exactly this. What I wrote down on the left-hand side is exactly the definition of the zeta function when you remember this boxed fact here that we wrote down. Okay. All right, and so that tells us, so this is 1 over it, so I'm going to take as my polynomial this, my LP of t is this polynomial. It's just some polynomial with integer coefficients. It's basically just the reciprocal of the characteristic polynomial of the matrix encoding the Frobenius action. And we'll note that this is the characteristic polynomial of a permutation matrix. Well, if you think about that for a minute, permutation matrices are orthogonal. Their roots all lie on the unit circle. And they also are reciprocal in the sense that if I have one eigenvalue, it's the inverse of that eigenvalue is also an eigenvalue. It's easy exercise to check that. And that completes our proof of the Weil conjectures. Okay, that wasn't so hard. All right. Let me just see how I'm doing on time here. Okay, we're good. Okay. So the last thing I want to mention before, well, two more things I want to mention before we leave our weight zero example. It's common to package all of these local zeta functions up into a global object called an L function. And these, in this case, what we're going to get is an Artin L function. And it can be written as an Euler product whose local factors can all be defined in terms of this L polynomial L sub p, at least at the good primes. Okay, we're not going to worry about putting in the Euler factors at the bad primes because there's only finitely many of them, and we're interested in statistical questions of distribution that allow us to ignore any finite set of primes. Okay, which makes analytic number theory a whole lot easier. Okay. Great. The last comment I wanted to make, actually, you know what? I think in the interest of time, I'm not going to do it. I'll just state it. Another question one might ask, in the very first slide I showed you, I wrote down NF of p values with over bounds b that were like 10 to the third, 10 to the sixth, 10 to the ninth. I think in the lecture notes I put 10 to the 12th. You might ask, how was I able to compute those so quickly? Well, there are very efficient algorithms for finding roots of polynomials over finite fields. And in fact, we don't even need an algorithm to find the roots of the polynomial over a finite field. All we need to know is how it splits, what its splitting pattern is, what are the degree of its irreducible factors. And one can compute the degree of its irreducible factors. So if I just take the GCD of a polynomial, say f, okay? So this polynomial here, the roots of this polynomial are exactly the elements of fp bar that are actually in fp to the r, because they're fixed by the Frobenius action. And if I compute this GCD, it's going to tell me exactly which roots of f are visible or are present over fp to the r. And I could easily count those. Now, the way I've written this down, this doesn't look especially easy to compute because I have some polynomial of degree p to the r. But I don't ever actually compute that polynomial. What I do instead is I start with the polynomial x, and I work in the polynomial ring fp x mod f, where f has some fixed degree d, and now I'm just going to compute powers of x. Compute x squared, x to the fourth, x to the eighth. I'll keep going all the way up until I've computed xp to the r. okay, using square and multiply algorithm, but I'm going to be reducing mod f all the way along. So I never have to work with polynomials of very large degree. And if you work this out, this gives you an algorithm that runs in time that's quasi-quadratic in log p. Okay, so very fast. So running time looks like, I should put a d in there too, but it's quasi-quadratic in the degree of the polynomial and the size of the logarithm, the size of the finite field. And if you think about if I wanted to write down this polynomial f, d log p is exactly the number of bits I would need to write it down. So this is a running time is quasi-quadratic. I should put a little epsilon in there. It's not, there's some other logarithmic factors I'm ignoring. Okay. All right. So great. I like dimension 0. It's easy to prove the Weil conjectures, and we have very fast algorithms for point counting. Life is good. Okay. So now we want to move to a dimension 1 example. And so now I will give the line that I would normally start my talks with, which is let E be an elliptic curve over Q, which we know we can always write in this form. And we'll now, so this is we're always, of course, interested in the smooth projective curve defined by this equation. And we have a distinguished rational point on our curve, the point at infinity. So as a projective curve, our distinguished point is always going to be this one. Okay. And we're going to be interested in primes of good reduction. So these are the primes where if we reduce A and B mod P, we get an elliptic curve over FP. And good here just means we want P to not divide the discriminant, which is negative, just means it needs to be odd and not divide the discriminant of the polynomial. Okay. And then we're going to define the quantity NE of P. Well, this is the number of points on our elliptic curve, or reduced elliptic curve, over finite field FP. And we know that this is an integer of the form, so that's a t, p plus 1 minus t sub p, where t sub p has absolute value at most 2 times the square root of p. Okay. And actually, well, this is a well-known theorem of Hasse, but it also follows from the Weil conjectures. If we had proved the Weil conjectures in dimension 1, we would know this as well, because the Riemann hypothesis would tell us this. Now, if we're interested in how this quantity NE sub p varies with p, well, the answer isn't so interesting because it goes to infinity, right? This is going to look like p plus 1 plus some error term that's on the order of the square root of p. So this is going to go to infinity as p tends to infinity. So this is different from our dimension 0 example where we were always getting some integer between 0 and d. So instead, we're going to focus on just the error term. So let's define xp to be the t sub p, call that the trace of Frobenius. We'll define that a little later. So this is going to be some real number between minus 2 and 2. So now we have an infinite sequence indexed by good primes of our elliptic curve. We have an infinite sequence of real numbers between minus 2 and 2. And the question is, how do they vary, or what's their distribution as we let p tend toward infinity? Okay, so now I want to pop up the computer here. Okay. Right, and I need to okay. So here's an example. So I've taken a particular elliptic curve y squared equals x cubed plus x plus 1. And for each prime of good reduction, I've gone and counted the number of points on that curve and subtracted off p plus 1 to get the trace Frobenius, t sub p, so that's some integer. And then I've divided by the square root of 2 to get x sub p. So that's some real number. And you can see that indeed they are all always between minus 2 and 2. Okay, does anyone see the pattern? No, no clear pattern. I don't know, maybe it's negative more often than it's positive, but yeah, no obvious pattern. As in our dimension 0 example, if we want to see the pattern, we really need to get more data. Okay? So here, So unlike in our dimension 0 example, there were only a finite number of possibilities. So it was easy to just count how many times each possibility got hit. But now we're talking about a distribution over the real interval from -2 to 2. So there are infinitely many possibilities. So instead what we're going to do is create a histogram where we're going to subdivide the interval from -2 to 2 up into subintervals. So this x-axis here, this is -2 over here, running up to 2 over here. And then I've partitioned it into a number of buckets. The number of buckets I've chosen is roughly the square root of the number of sample data points I have. So I get a data point for each prime up to some bound b. Here b is 2 to the 10th. So there are 170 data points that we have. Square root of that is about 13. So I subdivided this up into 13 intervals. And then I just count how many, for each of those subintervals, I count how many of the x sub p's lie in that subinterval. And then I put a bar on the graph whose height measures that count, or is proportional to it. And the gray line you see there, that's the uniform distribution. If everything was perfectly uniformly distributed, it would just be a blue rectangle filling in under the gray line. Now, so we've done this for primes going up to 2 to the 10th, and again, there's not really any obvious pattern. It seems to vary. But let's increase the bound on our prime, on our norm bound. Okay, so in each frame, I'm doubling the bound on b. And so the histogram, the subintervals are getting finer and finer because we're getting more and more data points. And you can see that as we let our bound b tend to infinity, we see the picture converging to a very nice, smooth, semicircular distribution. And I've also computed moments of the trace down here at the bottom. So these are the expected values of powers of the trace. And you'll see that the odd powers the distribution is symmetric, so the expected values of the odd powers always seems to be heading towards 0. And at the even powers, we're getting a sequence 1, 1, 2, 5, 14, and this time it is 42. And it would be a 0, and the next one is 132, and it keeps going in that way. These are, in fact, the Catalan numbers. And the remarkable thing about this is that it doesn't matter, as in with our cubic polynomial, if I picked a cubic polynomial at random, I would generally expect to see the same distribution. The same thing's true for elliptic curves. So let's pick another random elliptic curve. So this one here. Now actually that elliptic curve isn't random at all. This is a famous elliptic curve due to no Melky's that has rank 28. It's the largest rank of any known for any elliptic curve over Q. And the histogram is exactly the same setup. So we're going from -2 to 2. And you'll notice this graph here, when I only go up to 2 to the 10, looks very different. I have a huge skewing of traces towards one side. Actually, I should really be showing you the mirror image. This is showing minus the trace. So the fact that it has large rank means that it's going to tend to have more points than it should when I reduce mod p, at least when p is small. Because I have a lot of points over q, and those reduce to points mod p. And so you see a very skewed trace distribution at small primes. So maybe, for this curve, maybe the Sato-Tate conjecture doesn't hold. I mean, if there's going to be any curve that was going to violate it, this might be a good candidate. But let's see what happens as we let our bound go to infinity. And you can see, well, rank 28 doesn't mean much when p is heading towards 2 to the 40th. So it comes down to a nice smooth semicircle pretty quickly. And again, you'll see the moments down here at the bottom are converging to the sequence of Catalan numbers. Okay. Yeah, question? The graph I've been showing here is minus xp. So it's the normalized, so in other words, it's the normalized coefficient of the normalized linear coefficient of the characteristic polynomial for Frobenius. Okay. That convention is just when we go to characteristic polynomials of abelian varieties of higher dimension. Yeah, okay. Anyway, all right. So let's go back to our notes. So what I'd like to do in the last 10 minutes I have is explain to you why, even if you had never run that experiment, which I don't think Tate did, Sato certainly did, you would have predicted that you should see exactly that picture. And you would make exactly that prediction for exactly the same reason that if you were a number theorist and someone asked you, what should the distribution of nf of p be if f is a cubic, you'd sit down and think, it's S3 underneath, so I know what's going on in the background, and I could work out what the distribution should be from that. Okay. So why do we see this semicircular distribution? Why isn't it uniform? Well, it is uniform, but it's uniform with respect to a different measure. Okay? We want to understand that measure. Okay. So let's see. I think in the interest of time, I'm going to skip writing down the Weil conjectures in all their glory, even though they are a wonder to behold. I'll refer you to the notes for those. But what I will note is that what the Weil conjectures imply in the case of a curve, so now we're talking about a smooth projective variety of dimension 1. We have, so let's call our curve x, say, that's a big X. And our local zeta function of x is going to look like, so now the L polynomial is going to hop into the numerator. That's because we're now in odd dimension rather than even dimension. And the denominator always looks the same. It's not so interesting. Okay, and our L polynomial here, so this L polynomial is going to be an integer polynomial. It's going to have degree 2g, where g is the genus. And if you don't know what the genus is, you can take this as a definition. So if you take a smooth projective curve, you compute its zeta function, and lo and behold, you find out it's a rational function, and the polynomial in the numerator has some degree. Divide that degree by 2, that's your genus. Okay. And it has roots of absolute value p to the minus 1/2, and it's reciprocal, meaning that if I take the inverses, I get roots as well. And in the case of an elliptic curve, what does the L polynomial look like? Well, it's going to look like this. So it's not quite the characteristic polynomial of Frobenius, it's the reversed characteristic polynomial. Okay. And the number of rational points over at p is going to look like, sorry, I should put an e here now, an e of p. This is going to be precisely p plus 1 minus tp, as we saw. Now, we now want to consider as we did with our Frobenius traces that we normalized by dividing the square root of p, we're going to normalize these L polynomials. So we're going to replace t with t over the square root of p. Okay, so in the case of our elliptic curve, that means we're going to get something that just looks like t squared minus, I should write it this way, t. So just some quadratic polynomial with only one coefficient that we don't know, this a1. And this is minus the normalized trace of Frobenius. So a1 is some real number between minus 2 and 2. Okay, so what do we know about this normalized polynomial, L polynomial? Well, it has roots on the unit circle. It's monic. It has roots on the unit circle. So, monic, roots on the unit circle. And they come in conjugate pairs. Because it's a real polynomial, and I know that if one thing is a root, so is its inverse. Okay. All right. Well, so if we're looking for now we're trying to find some group, some Sato-Tate group that's going to explain the distribution of these L polynomials, right? If when we in our weight 0 example, we took the Artin representation, we got this group, this matrix group, this finite matrix group, and we only focused on the trace, but we could even define an L polynomial for our in terms of the zeta function of our dimension 0 variety. And the distribution of those L polynomials that we see, they're all characteristic polynomials of permutation matrices. Okay, so, and they come from taking characteristic polynomials with respect to a particular Sato-Tate group, a permutation group, and their distribution is given by the Haar measure on that group. More precisely, if we take the Haar measure on the group, push forward to conjugacy classes, which are characterized by their characteristic polynomials, that tells us exactly how often we see each characteristic polynomial. So what group should we be looking for here? Well, we want characteristic polynomials that are, in the case of an elliptic curve, that are quadratic. So that suggests that our G sub E, our Sato-Tate group, should be a matrix in GL2C. So this is just implied by the fact that we want degree 2. Now, the fact that it's monic and satisfies our functional equation, meaning the constant term is going to be 1, meaning determinant 1, means that we should really be looking inside SL2. And the fact that its roots lie on the unit circle tells us, and this is coming from the Riemann hypothesis, tells us that we really need to be looking for a subgroup of SU2. But once we're inside SU2, the characteristic polynomials that we get, they all look like polynomials that could be normalized L polynomials. They all look like the normalization of some Weil polynomial. And so we would say generically, we might conjecture that G sub E should be, in fact, equal to SU2. Just as in the weight 0 case, we conjectured that we should generically see S3. And what do we mean by generic? Well, in the case of elliptic curves, what a generic is going to mean is that we have no extra endomorphisms even over the algebraic closure. It's known as saying no CM. For abelian varieties of higher dimension, we're going to want a different notion of generic. This is not strong enough in general, but it is strong enough in dimension 1. Okay. And then the Sato-Tate conjecture says the following. So let E be an elliptic curve over Q without CM. Okay, and the statement is that the sequence of normalized Frobenius traces which I denoted X sub P, and here I'm always assuming that P is a prime of good reduction, but actually it doesn't matter because whatever values it takes at the bad reduction aren't going to change distribution quantities. This sequence is equidistributed on the interval -2 to 2 with respect to the push forward of the Haar measure on SU2. And I'm going to explain exactly what that means in more detail in the next lecture, but I'll just note a consequence that's also equivalent. In particular, for any subinterval, say A to B, sitting inside -2 to 2, if I take the limit as B goes to infinity of this ratio, so I want to count how many of my X sub P's fall in this subinterval over how many X sub P's I have with P bounded by B. This is always going to be 1 over 2 pi times the integral from A to B, the square root of 4 minus t squared dt. And that's where the semicircle comes from. Okay. And we can also compute moments. So the expected value of the trace, nth power of the trace, this is going to be, well, how do we compute an expected value? We integrate against the Haar measure, as we'll see next time. The Haar measure on SU2, well, it looks in terms of, can be expressed in terms of eigenangles. And in terms of eigenangles, it looks like sine squared theta d theta. And what I'm integrating, I want the trace, that's going to be 2 cosine theta, and I want its nth power. Okay. Yes, thank you. Okay. All right. And this is a great exercise in to give to your first year calculus students. And we find that this integral is 0 when n is odd. Yes, integration by parts. Yeah, that was the phrase I was looking for. Okay, and then when n is even, we find that we get the 2mth, or the mth Catalan number when n is 2m. Okay, and so the sequence of, the moment sequence looks like 1, 0, 1, 2, 0, 5. Okay. Exactly the moments that we saw on the screen. And I will end there unless there are any questions.
Are there any questions?
I was wondering if, sure. I was wondering if there is anything known about curves with complex multiplication.
Excellent question. Come to this afternoon's lecture. We will prove everything there is to know about such curves. Well, about their Sato-Tate distributions.
Other questions?
Hey, maybe I'm misunderstanding, but it seems like, are you choosing an embedding of QL into C when you talk about all of these things?
Yes, come to the third lecture.
Okay.
Yeah, you're getting ahead of me. But well, there's a couple of different ways to define the Sato-Tate group. Sarah gives two. One is a motivic version, another is an alatic version. We're going to work through in excruciating details exactly how one defines the Sato-Tate group using the alatic representation attached to an abelian variety. And yes, it will involve choosing an embedding into C. We'll prove that that choice of embedding doesn't make any difference if the dimension is at most 3. And we'll choose that certain properties of the Sato-Tate group are independent of that choice regardless in all dimensions, and I'll enumerate exactly which those are.
Any more questions?
You showed these super cool animated histograms. Could you say some words about how fast they converge to the distribution? Does it depend on the elliptic curves that you're working with? Or?
Yeah, so that is also an excellent question, especially in the context of this week's program. So there are some theoretical results that are known. In the case, if you're willing to assume GRH, you can say some things about the error term. In fact, I think I give a reference to at least, I think, 2 papers, one by Alina Bukur and Karen Kadlai, and another by Jesse Thorner that talk about exactly this question. But they're fairly coarse estimates. There certainly is going to be a dependence on the conductor in there somewhere, but I think that's a very subtle thing to try and track down. There's a lot of number theory. I mean, a lot of this is tied to questions about BSD, and there are many other places one could go with this. So studying the error term in the Sato-Tate distributions is a wide open area of research. We know very little, and what we do know at this moment is pretty much all dependent on assuming GRH.
Any more questions? Okay, let's thank Drew again.